Okay, so let's generalize what we studied about binomial distribution and Bernoulli trials in the last class. We basically generalized our very discussion on binomial distribution. What was that? If you consider an experiment with n Bernoulli trials, okay, so basically there is a dichotomous experiment, and that particular experiment under identical conditions is being performed n times. That means there are n trials of this experiment being performed, and they are Bernoulli trials. That means they are independent, first of all, finitely many in number, because n is going to be a finite number. In other situation, it is also saying that the very possible outcomes related to each very trial is exactly the same. They are exactly two outcomes because the experiment itself is dichotomous. One is my success, one is failure. And the fourth condition says that the probability of success and probability of failure in each trial is a constant. So whatever is probability of success in the first trial, it is throughout the n trials, it's the same probability of success. Whatever is probability of failure in the first trial, throughout it is the same on all the n trials. So that is what is my n Bernoulli trials. So consider an experiment of n Bernoulli trials. Now when you do that, you basically obtain a random variable which represents the number of successes in each outcome concerning with all the trials, right? Wherein x is a random variable which assigns to each outcome the number of successes in it. Okay? So basically, if your experiment is being performed 5 times, that means the same experiment is being performed 5 times, you consider then the experiment of these 5 Bernoulli trials. Now when you are going to consider this experiment of 5 Bernoulli trials, what are you going to see? When you do that, what will be your outcomes? You can get success in the first trial, success in the second, success in the third, success in the fourth, success in the fifth. You can get success in the first, failure in the second, success in the third, success in the fourth, success in the fifth. Or you can get, success in the first, failure in the second, failure third, success, success. So many of these I can get, right? So when you consider this experiment of 5 Bernoulli trials, in this situation you get a lot of outcomes corresponding to the success and failures as outcomes. Are you understanding? So like this is one of the outcomes, this is another, and so on, right? So basically I'm talking about a random variable which is assigning to each of these outcomes the number of successes in them. Now, if x is doing this job, if a random experiment of 5 Bernoulli trials or say n Bernoulli trials is being performed, then what do you think? How many successes minimum and how many successes maximum can you get? Minimum to minimum, it can happen that in all the trials you are getting failure and therefore no success occurs. You can have exactly 1 success occurring. Then you can have 2 successes occurring when in any 2 of the trials you are getting success and in rest of the time you are getting failure. After that you can get 3 successes occurring, 4 and so on when in all the n trials you get success. That means all n are successes. That means this capital N or this capital X, which is standing to represent the number of successes in each outcome, can vary from 0 to n. So then capital X assumes values 0, 1, 2, 3 up till n. The moment I have got the values which x can take, I am only concerned with the respective probabilities. With the probability of x being equal to small r where R is any one of these numbers. This is representing probability of R successes occurring. What is the probability that number of successes is R? I already told you. In the last class we understood that probability of x equals 0 was the first term of the binomial expansion q plus p whole to the power n. Probability of x equals 1 was the second term of the binomial expansion q plus p whole to the power n. Probability of x equals r is equal to the r plus 1th term of the binomial expansion p plus q whole to the power n. So, what would this be? R plus 1th term of q plus p whole to the power n, where n is the number of Bernoulli trials, p is probability of success in any trial, any one trial, probability of success is p, and q is probability of failure in any trial. And therefore, from here you can clearly say p plus q is 1. So, r plus 1th term of q plus p whole to the power n. You all know that if I talk about x plus y whole to the power n, then what is the r plus 1th term of this expansion? Isn't it NCR x to the power n minus r y to the power r? We have done this in binomial, right? So, r plus 1th term of q plus p whole to the power n will be NCR q to the power n minus r p to the power r. This happens to be the probability of capital X equals r, and r is varying from 0 to n over all these values. And thus, once you have got all the values which capital X is assuming and you have also got their respective probabilities, you have actually got your probability distribution. Then, and we already verified this to be the probability distribution in the last class. We are going to discuss it again. This is capital X, this is P of X. So, you have 0, 1, 2 and so on, n. These are the n values. And what is the P of X? It is NC0 q to the power n minus 0 p to the power 0. What is the probability of capital X equals 1? It is NC1 q to the power n minus 1 p to the power 1. What is probability of capital X equals 2? NC2 q to the power n minus 2 p to the power 2. What is the probability of capital X equals n? It is NCn q to the power n minus n p to the power n. Fine. Can I say that this is my probability distribution of the random variable capital X? Yes, because when you add these probabilities, actually you are obtaining the binomial expansion of q plus p whole to the power n, because its terms only are written over here. Just if you incorporate plus sign in between every term, you will be getting the entire expansion of q plus p whole to the power n, and q plus p is equal to 1. So, 1 to the power n will give you 1. That means this sum is going to give you 1, and therefore, this is the probability. This is the probability distribution of capital X. But because in this probability distribution of the random variable capital X, the probability of each of these values, probability corresponding to each of these values is nothing but terms of a binomial expansion. That is why this is known as binomial distribution of capital X, or you say X follows a binomial distribution. X is a random variable whose probability distribution, if looks like this, wherein the probabilities are nothing but terms of binomial expansion q plus p whole to the power n, is said to follow a binomial distribution. Or you can say that x is a binomial variate with parameters n and p. Yes, this is the only thing which is important. If you know capital X is a binomial variate, in order to get its binomial distribution, you already know that if there are n Bernoulli trials being performed, then already you can write these values from 0 to n. In order to compute these probabilities, what you need is the value of n and the value of p. You don't need the value of q because q is 1 minus p only. So if you know p, you already know q. So you know p, q and n, and with these three values, you can compute all the probabilities and hence get this complete binomial distribution. So what all do you need actually to write the binomial distribution of a binomial variate capital X? The information of n, so that you get to know how many Bernoulli trials are there, so that you can write from 0 to that particular number as the values of this random variable. After n, you also need the value of p, which is the probability of success in any trial, so that you have n with you have p with you, from that you can evaluate q, and hence by plugging in all those particular data in these particular values, you can get the probabilities, and hence your complete binomial distribution will be completed. So only two things are enough to get you this particular table. One is n, one is p, and that is why n and p are said to be parameters of this binomial variate capital X. Is it clear? In here we say that a binomial distribution, any binomial distribution is known by these two parameters, okay. So a binomial distribution with n Bernoulli trials, so n is important, n Bernoulli trials. A binomial distribution with n Bernoulli trials and small p being equal to probability of success in any trial is denoted by b n comma p. It is the value of n, it is the value of p, which actually is enough to give you a binomial distribution. Is it clear? So instead of writing this binomial distribution of capital X, you write it by BNP notation. Fine. So if I talk about the application of this, let's see how actually this works. The question is that a coin is tossed 5 times. Find the probability of at least 3 successes. This is the probability of 0 success, this is the probability of 1 success, this is probability of 2 success, and so on. This is probability of achieving n successes in n Bernoulli trials. Right now 5 times a coin is being tossed. Let's write the random experiment is tossing a coin. This you already know is a dichotomous experiment. 5 trials are being performed. 5 is a finite number. In each trial you are getting either a head or a tail as the outcome. Because I am being asked at least 3 successes, I am saying let this be success, let this be failure. It's given in the question. A coin is tossed 5 times, find the probability of at least 3 heads. Question is this, at least 3 heads. And we find probability of successes. That means the question is indirectly saying to consider the outcome of head as a success and outcome of tail as a failure. So in these 5 trials, the finite number is 5. Then there are 2 outcomes associated with each trial, head and a tail. They are independent trials obviously. And what is probability of success in any one trial? Half, and probability of failure will therefore be 1 minus half, which is half. So these trials clearly are my Bernoulli trials. Here basically starts with the first question. What happens to be my first question? First question in here is for 1 mark. We are discussing the CBSE pattern question exercises for probability class 12th. First question for 1 mark is giving us 2 events, event A and event B, such that probability of occurrence of event A is half. Occurrence of event B has probability 7 by 12 and probability of not A or not B is given to be 1 by 4. State whether A and B are independent or not. When do you say 2 events are independent? When occurrence or happening of one event does not affect the probability of occurrence or non-occurrence of the other event. In that situation, what happens is, suppose A and B are 2 events, probability of A when B has already happened is going to be equal to probability of A itself, because happening or not happening of B is absolutely not affecting the probability of happening of A. So whether B has happened or not happened, probability of A when B has happened or probability of A when B has not happened remains the same. Similarly, probability of B by A happens to be equal to probability of B. That means probability of happening of B when A has already happened or probability of happening of B when A has not happened, they are the same, because happening or not happening of A does not affect the probability of happening of B. Because of these facts related to 2 events being independent, I get probability of A intersection B to be equal to probability of A into probability of B, provided A and B are independent. That means if I have to show that A and B are independent, I have to come to the conclusion regarding A and B that whatever is the probability of their intersection, that is equal to the product of their individual probabilities. If these 2 probabilities come out to be equal, I get that A and B are independent, and if they happen to be unequal, I say that A and B are not independent. So let's begin with watching out the conclusion regarding the independence of the 2 events A and B. Probability of A is this, B is this, probability of not A or not B is 1 by 4. How do you write that? Not A means A bar, or means union, not B means B bar. Not A or not B. This is given to be 1 by 4. By the De Morgan's law, we know that A complement union B complement is A intersection B whole complement. Whatever was the meaning of complement in the chapter sets, same is the meaning of the bar over here upon the alphabets A and B. So probability of A bar union B bar is probability of A intersection B whole bar, just by De Morgan's law. This is 1 by 4. What is this? This is probability of not happening of the event A intersection B. Probability of not happening of an event is 1 minus probability of happening of that event. That is 1 by 4, and therefore I get 1 minus 1 by 4 to be probability of A intersection B, which is 3 by 4. Fine. One thing we've got. What about probability of A into probability of B? Probability of A is given to be half. Probability of B is 7 by 12. So you get 7 by 24 as the product of the individual probabilities of A and B, which is absolutely not equal to 3 by 4, which is probability of simultaneous occurrence of A and B. And thus A and B fail to be independent events. Is it understood? They are absolutely not independent, because probability of simultaneous occurrence of A and B is 3 by 4, but the product of their individual probabilities is 7 by 24, which is unequal. Moving to the next question, we have for 2 marks coming that a couple has 2 children. Find the probability that both are boys if it is known that the older child is a boy. Okay, so if a couple has 2 children and we are wanting to find out the probability that both the children are boys, given that older child is a boy, how do you start your question with? Sample space, what would that be? 2 children are born. It can happen that first child is a boy, second is also a boy, okay? Or it can happen that first is a boy, second is a girl. Or it can happen that first is a girl, second is a boy, or it can happen first is a girl, second is a girl. So you know in what sense have I written B1, B2, G1, G2. B1 means first child is a boy, G2 means second child is a girl, B2 means second child is a boy, G1 means first child is a girl. Okay? This is what happens to be the sample space corresponding to two children being born to a couple. Now here it is saying, find the probability that both are boys. Suppose I say my event A is that both the children are boys. And I am defining another event that older child is a boy. Now let's see what happens to be the elementary events favorable to these events. Both are boys. This is the elementary event favorable to event A. Fine. Both the children are boys. Apart from this, is there any other elementary event favorable to event A? No. In all the rest of the elementary events, there is at least one girl definitely being born to the couple. I am interested in the elementary event which supports or favors that both the children born are boys. So only this elementary event does that. So this will be a singleton set consisting of B1, B2 elementary event. Next I have older child is a boy. You can see first child is a boy, second is a boy. First is a boy, second is a girl. First is a girl, second is a boy, first is a girl, second is a girl. Obviously the child born first would be older. I am given that the older child is a boy. That means only this and this I can select as the elementary events favorable to my event B, because only in these two cases the boy is being born before the next child. So older child is definitely a boy. So I have B1, B2 and B1, G2. I am being asked what is the probability that both are boys when it is known that older child is a boy. Isn't this beautiful? How actually a practical scenario gets boiled down to a conditional probability question. What is the probability that both the children are boys when you know that older child is a boy? What is the formula? This is probability of A intersection B upon probability of B. Or I can also say this is also equal to number of elements in A intersection B upon number of elements in B. When you divide the numerator and denominator by number of elements in the sample space, you obtain this as your very formula for P of A by B. How many elements are there in A intersection B? If you talk about this is A, this is B, then clearly A intersection B consists of just B1, B2, isn't it? Only one element is common. So number of elements in A intersection B is 1. Number of elements in B, event B has 2. So 1 by 2 happens to be the probability of both the children being boys when you know that the older child is a boy. Is it clear? Easy enough? Next question, let's see what is it. The probability that a teacher will give an unannounced test during any class meeting is 1 by 5. If a student is absent twice, what is the probability that he will miss at least one test? Now let's say that E1 is the event that student misses the first test. Student misses the first test. And let's say E2 is the event that the same student misses the second test, because he is absent twice. Now see, teacher is giving an unannounced test during any class is holding probability 1 by 5. If a student is absent twice in that class, then what is the probability that he misses the first test? One day he is absent, that day he can miss a test only if the teacher decides to take the test on that day. The probability that the teacher is going to take the test on that day is 1 by 5. Same is the probability that the student will miss the test on that day. Obviously, if he is absent on a certain day and the teacher is not taking a test on that day, how can he miss the test? He can miss a test on a particular day when he is absent only when the teacher decides to take the test on that day, and that holds probability 1 by 5 that she is going to take a test on a particular day. If that is 1 by 5, then that is the same probability of the student missing the first test. So, probability of happening of event E1 is 1 by 5. Similarly, he can miss the second test only when the teacher decides to take the second test on the day when he is absent. Fine? And a teacher holds probability 1 by 5 of taking that unannounced test. So, the student missing that test is again 1 by 5. So, probability of event E2 is also 1 by 5. Tell me one thing. Are E1 and E2 independent events or not independent events? If a student is missing the first test on a certain day, does it hold any contribution towards the probability of the student, same student missing the second test on some other day? Of course, these two are unaffected events. If he has missed the first test on a certain day, how is that going to be affecting the probability that he's going to miss a second test or vice versa? Clearly, E1 and E2 are independent events. They are independent events. If that's the scenario, what is the probability of E1 intersection E2? You all know this is equal to probability of E1 into probability of E2. Fine. This is something you need to keep in mind because they are independent events. I am being asked what is the probability that he will miss at least one test. He is missing the first test is event E1, he is missing the second test is event E2, so he will miss at least one test, means he will either miss the first test or he misses the second test. So either E1 occurs or E2 occurs is the event whose probability needs to be computed, that is being asked in the question. Okay, so you need to correctly decode what is that event whose probability the question is indirectly or in statement form asking you to compute. What is this? This is probability of E1 plus probability of E2 minus probability of E1 intersection E2. Probability of E1 is 1 by 5. This is again 1 by 5. What is this? This is probability of E1 into probability of E2, which is 1 by 5 into 1 by 5. This is 2 by 5 minus 1 by 25. This happens to be 9 by 25. If you don't like it this way, you can also compute this in other fashion. Probability of E1 union E2 is 1 minus probability of not happening of E1 union E2. Right? What is this? By De Morgan's law, this is probability of E1 bar intersection E2 bar. Now you know we have done this result in our theory lecture that if E1 and E2 are two independent events, then their bars are also independent events. So clearly this is equal to 1 minus probability of E1 bar into probability of E2 bar. Probability of E1 is 1 by 5, so probability of not happening of E1 is 1 minus 1 by 5. Probability of happening of E2 is 1 by 5, so probability of not happening of E2 is 1 minus 1 by 5. This again is going to give you 9 by 25. Is it clear? That's how you attempt this question. Okay? Moving to the next, we have for 4 marks. Probability of A is given, B is given, A intersection B is given. Find probability of A bar by B bar and probability of B bar by A bar. Let's try to do that. Okay, so probability of A bar by B bar. Just apply the definition of conditional probability. This is equal to probability of A bar intersection B bar upon probability of B bar. Right? What is this? By De Morgan's law, A union B whole bar upon probability of B bar. Not happening of event A union B, not happening of event B. What are their probabilities? 1 minus probability of happening of the respective events. This is 1 minus probability of happening of A union B, 1 minus probability of happening of event B. In here, this is probability of A plus probability of B minus probability of A intersection B, and this is 1 minus probability of B. What is this? Probability of A is given to be 3 by 8. Probability of B is 1 by 2. So you have 3 by 8 plus 1 by 2 minus 1 by 4 whole upon 1 minus probability of B is 1 by 2.